Hello, welcome back to our review session. All right, so we're going to talk about a different combined loading problem, the rectangular post. Okay, so here I have a rectangular post as shown. All right, and I have a complex loading, as the red arrows indicated here, here, and here. All right, so I want to find out stresses at point H and point K. Stresses point H and point K. So what I do is I first make a cut right here, okay, right here, cross my H and K, and this is actually showing here already, okay. So I want to examine what type of force I will see on this cut. So here, after cut, is my leftover section. Okay, here is my foundation. Okay, actually my foundation looks a bit not right, so let me extend it a little bit. Okay. Okay, don't really like this. I'm so sorry. I just want to make it right. So let's make it right. Okay, so now this is H and this is K. I'm going to move first these forces. This is axial force right here to the middle of it. Okay, well, by moving that, basically I introduce the moment. All right, I introduce the moment. Since it's shifting, right, shifting close, right, to the x direction, I actually introduce the moment on the mx direction. Okay, and then also once I shift the other forces, which is 95 kilonewton, back here to the H. So I have here, so this is 210, this is 95. And when I shift this way, I also added another moment. Okay, so what type of moment I added a negative moment going this way. Okay, going this way. Okay, can you see it? So I'm added a moment going this way. Then I'm also moving my 65 kilonewton, which is here, close to this section here. Okay, so when I move it, this is basically 65. Okay, I'm introducing a moment in the z direction. In this way. Okay, so after I make these shifts, what I'm doing, basically I made the cut first and shift all my forces on this section and consider all the shifted distance, introduce the moments. So I look at the cross section and make a list. So axial force wise, I have Py. Okay, of course Px is 0, so I don't have any axial force in terms of x. So Py, which is on the cross section, equal to a negative 210 kilonewton. Okay, so this is Py, right? Negative 210 kilonewton. Right? I also have a shear force, right? So Vx equal to a negative 65 kilonewton. And Vy is 0, right? Because I don't have a y, I have a Vz direction, which is negative 95 kilonewton. Okay, so this is axial shear. Okay, and what else? I have a bending moment. Mx equal to a what? Equal to a mx 210 minus mx or plus mx 95. Specifically, I have a 210 multiply by what? Multiply by the shifted distance, which is actually a 50 millimeter. Be careful. Okay, and minus a 95 kilonewton multiplied by shifted distance of how much? 150 millimeter. Okay, so these are the moments I have. And don't forget, I also have a Z moment, okay, which is actually 65 kilonewton. 65 kilonewton. And this is my 65 shifted by 150 as well. Okay, so these are the moments. These are the moments. How about My? I fortunately don't have any My. Don't have any My. All right. So these are the external forces, and then you can follow the correct solution to find the stresses, right? To find the stresses. Okay. Just be careful though. Be careful though. The shear stress on point H here, right? The shear stress on point H here from the x direction. Right? From Vx, this is x, right? And this is z. Y is actually pointing out towards the plane. So Vx is going this way. Okay? Vx has the maximum shear stress to H. So tau H equal to Vx QHIT, if I want to draw it. Right? But this is due to Vx. The shear stress generated from Vz, right? Vz, which is this way, right? Is what? Is what? What is the shear stress generated on H from Vz? Right? So going this way, I'm on the edge. Don't forget, I'm on the edge. So QH on VZ equal to 0. So this is a big 0. Okay, so not necessarily you have the shear stress generated from shear force. It depends on the location. All right, depends on the location. Okay, so this is the tip. This is a tip. Okay, so you have to be careful on the location. On the location. All right. Okay. Good. Okay. So after this, right? After this, let's take a look at the circular post problem. Circular post problem. All right. For a circular post, all right, I will also try to do the same thing. I will make a cut here. Okay, and then after make the cut, of course, I establish a local coordinate system. I would shift my forces all the way back here to the center of it. Okay, and by doing the shift, I move these forces, say 2,350 Newton first through 90 millimeter. So when I do that, this is the force, and move this way, this is 90 millimeter. When I do that, I introduce a moment on the x direction, so mx 2350, all right, equal to 2350 Newton multiplied by a distance 90 millimeter. Okay, so that is the moment caused by 2,350 Newton with respect to x-axis. Okay, and don't forget, I also have to move a distance of this much to the cross section. So I will also introduce a moment in the y direction, let me use a different color here. My equal to 2350 Newton multiplied by the distance here, which is 50 plus 105 millimeter. Okay, and of course I have my shear Vz equal to 23509 Newton. Okay, so that's how much external force I have from the 2350 Newton. Similarly, I will take a look at the forces. From this 1,275 Newton. Okay, so when I move this 1,205 Newton, it is naturally equal to Vy. When I move that, I'll also cause the moment in the z direction. So Mz 1,275 Newton equal to 1,275 Newton multiplied by the distance moved, so 55 plus 105 millimeter. Okay, but when I move this force, I also shifted along the 90 millimeter direction. Okay, so I shifted by around 90 millimeter. So what kind of moment I will generate by that? What kind of moment I'll generate by that? Okay, be careful. Since I'm moving along the force direction, right? I'm moving along the force direction. So along the force direction, I do not introduce any moment. I do not introduce any moment. Okay, so I will only have a moment generated by the 1,275 newtons. Okay, so these are all the forces I have on the core section. So I'm making a list here. So the shear force I have Vz equal to 2350 Newton, Vy Newton. Moment I have My caused by 2350 equal to a 2350 Newton multiplied by 50 plus 105, so 60 millimeter. And My, sorry, freeze on me. Sorry, this is supposed to be Mz. Mx 2350 equal to 2350 Newton multiplied by 90 millimeter. And Mz equal to a okay. So these are the external forces I will have on my system. These are the external forces to have on my system. Now, looking at the cross section here, again, I have a shaft. So this is H, this is K. Okay, so Vz, let's take a look at the K here, sorry, H here. This is my neutral axis. Okay, well, I shouldn't say this because it depends on the forces, right? So actually, let's take a look. So first, Vz, and coordinate system here is Y. Coordinate system here is Z. X is actually pointing outwards. Okay, so Vz will give you a shear force at H here. So tall H will equal to Vz QH divided by IT. And guess what? The Q for this case is actually 0, so I have a 0 shear stress generated by Vz. How about Vy? Now Vy is actually this way, so tau h Vy equal to Vy QH IT, but for this case, I do have a QH, and which is actually listed in blue. Okay, how about my? So my basically will generate a bending moment, right? So I have a tensile stress generated by my equal to my r divided by I. Okay, how about mx? Mx is actually going in terms of torsion. So I have a shear stress generated by torsion equal to mx r over j. Okay, and by the way, this is tau h mx. Okay, how about mz? So mz basically gives me a what? mz gives me a normal stress. But since I'm on the neutral axis here, distance 0, 0. So on this point here, I will have a shear stress caused by mx. I will have a normal stress caused by my. I'll also have a torsion-induced shear stress caused by mx and a normal bending-induced shear stress caused by vy. And that is going upwards. Use blue. Canceling mx. Okay, let me complete the rest of the stress. Okay, so this is the stress state for that element H. Okay, then you can use the Mohr circle to find out the principal stress for this point. Okay, so now I'll upload all these problems to Canvas with my notes again. Okay, but you realize that the combined loading is fairly complex. So I suggest you go over all the problem we posted and have a grasp of it. Okay, you're welcome to send me email or call me to discuss further.